So thanks everyone for joining. I'm going to start by sharing my screen. My name is Erin Diel. I'm an application specialist with Glencoe Software. There is an intro video from Chris Allen, our VP of Software Engineering, on the sort of intro day one page if you're not familiar with Glencoe Software. But just to say briefly here, we are the exclusive commercial partner of the Open Microscopy environment. So we work really closely with a lot of people on the OME team. A number of people who work at Glencoe have been previous OME team members. So there's a lot of really nice overlap and collaboration there. And so what I'm going to share with you today, I wanted to generally speak about the kind of derived data from our images, like segmentation and classification, and those segmented or classified objects, the measurements that we make of them and how we represent those in OMERO. And so there's a few tools that I'm going to talk about that I think are either things that are familiar to those of you who are using OMERO and things that might come up across the meeting and might have come up in previous OME meetings. So the first is the idea of OMERO tables. This is one kind of metadata in OMERO that you can store denser sort of tabular analytical data. And so we'll make use of OMERO tables today. The next is the idea of a microservice architecture. So I know this has been a topic at previous OME meetings, and Glencoe has done a lot of work to develop a few different microservices that perform various functions, but the one that I'll talk about today will be responsible for serving the tiles for images and this sort of derived mask or label image data that I'll show in a moment, but providing these tiles in a viewing context. The final piece that will be relevant for this demo is the concept of next generation file formats. And so the OME team has done a lot of work to build a specification for OME-ZAR. And this is the data structure that I'll refer to today that we're using for these masks or label images. And we'll talk a little bit more about what those are if they're not a kind of data that you've worked with before. And the OME-ZAR specification is what we're following to store that data and show it to you in the viewer. The last piece, the viewer that I'll use today, is called PathViewer, and this is a product from Glencoe Software. It's built with digital pathology and whole slide images in mind. And I want to emphasize that although this is a proprietary product from Glencoe Software, first we have a number of people who are using this on top of an open source OMERO installation. And the second is that the data structures that I'll talk about today for this derived data, like OMERO tables and OME-ZAR, are also very compatible with open source viewers. And one example of this is Nipari. The OME team has done a lot of work to provide a plugin, OME-ZAR, to be able to open OME-ZAR data in Nipari as an example. And that's compatible with both images and the segmentation data that I'll show today. So you'll see it in PathViewer today and some of the workflows that we've built into both OMERO and PathViewer. But we're happy to talk about across this meeting other ways, and I'm sure the OME team will be as well, other ways to build visualizations like these. Okay, great. So hopefully you see my OMERO web view here. I have an OME Meeting 2021 group here, and I've gone ahead and imported just two files, two SVS files from the Cancer Genome Atlas. And you can see if you've worked with whole slide images before, digital pathology data before, you're familiar with the idea that although these are two SVS files, these files frequently have the tissue scan itself, but also some image metadata like label image data and a macro view of the slide. Okay, so that's why you see, in fact, 6 images listed here. Okay, so I'm going to double click on one of these thumbnails, and just like you might work with tools like iViewer and other viewers within OMERO, if I double click on it, it opens up in this viewer that I described, PathViewer. Okay. So for those of you who haven't used PathViewer before, I just want to orient you a little bit to this user interface. So on the left-hand side, I have those 2 tissue scans that I mentioned that I had imported into this particular group. And one difference in OMERO Web is that I just see a listing of 2 images here instead of the 6 that I saw in the previous view. But I do still have a representation of the label and macro image. If I minimize my bird's eye view here, I can see the label and macro images drop down, and that's where those images are in that drop down on the right. Okay. I also have a viewing options tab. So for RGB data, we frequently just represent this as a brightness slider, a single slider. But if you have fluorescence data, we also have a channel specific representation. So even in this data, it is of course RGB, and so it is 3-channel image data. And if I hit the advanced button here, then I see these 3 individual channels. And so you could think of this similar to your fluorescence data. If you have, DAPI, Sci3, and Sci5, you can edit the rendering settings for each channel specifically in this left-hand viewing options panel. Okay, I'll go back to my RGB view. Okay. And then in the center, I have the image data itself. And along the top here, I have a variety of annotation tools, rotation, zoom. So all the ability to explore this image data, zoom in, pan around. And importantly, one of the things that will come up not only for image data, I'm just going to hide this ROI. One thing that will come up not only for this image data, but the derived segmentation data that we'll talk about is that this image, either in its SVS form or in this OMERO specification, is quite large in X and Y, and therefore necessarily has a representation not only of image tiles, so a tile in this part of the image, a tile here. You can think of this as sort of at the acquisition level as well, how you acquire this image in tiles. But it also has a representation of multiple scales. So you have the original, full resolution array that could be quite large for some digital pathology data. This is easily 100K by 100K pixels. And so many file types that support this kind of data have a pyramid of resolutions, that original array downsampled any number of times to form a pyramid of smaller and larger arrays. And so in PathViewer, as I explore this image data, here when I'm all the way zoomed out, I need to look at all of the data in X and Y, but I don't need to look at the highest resolution array. So I can take that very downsampled version of the data, and yet I want to load all of the tiles. But as I zoom in, I want to maybe look at the highest resolution data now, but I only have to look at maybe 1 or 2 neighboring tiles in order to get this particular view, because I'm spatially restricted in X and Y. I don't need to look at this tile down here in the bottom right-hand corner because it's not in view currently. Okay, and I'm emphasizing that because, as I said, it'll come up again when we think about how to represent the segmentation of this original image data. Okay, so I'm going to turn on one ROI region of interest annotation that I've made on this data already. So this was with these annotation tools in PathViewer. And this is an outline of the tissue itself. And essentially the workflow here that many of you might have done before is you're going to outline your tissue of interest, or maybe even a smaller subregion, and then you're going to segment the objects inside that region. And so here I'm going to do a nuclear segmentation where it's going to try and find all the nuclei within this tissue region here. And so then the question is, how do we represent the output of that segmentation in this viewer such as PathViewer? Okay. To give you one idea of how you might do this to contrast with what I'll show you was sort of our ultimate implementation, I'm just going to hop over to this other image where you can already see I have a higher number of ROIs here. So I'm going to hide my entire tissue outline and hop to this small tile here. So I annotated a smaller region, and then I ran a segmentation within that region. The segmentation tool that I'm going to use throughout these examples is called StarDist. This is a deep learning method for nuclear segmentation, and I use some of their pre-trained models that you can find on their GitHub. Okay. So StarDist was used to find all of these nuclei, and essentially each of these entries in this list here is one of those polygons, okay? And each of these polygons is represented by 32 coordinate points, okay? And this is a perfectly fine way to represent this nuclear segmentation. I can clearly see each individual object here, and I can even interrogate each one specifically. So here I'm highlighting one of them, and I could, adjust this polygon. I could change its color. I could do various things to change its visualization. And the issue here is that if I consider the entirety of this image for a number of reasons in the way that these tools currently work, this doesn't scale to the entirety of this tissue section. So if I were to segment the entire section instead of this small region, I would easily have tens of thousands, if not hundreds of thousands of objects. And for those of you who are working with digital pathology or other whole slide image data, you know this very well, that a segmentation can easily be, you know, in the tens or hundreds of thousands of objects, and how to represent that data can be a challenge. And so one sort of surface level reason why this might be a challenge is because imagine here I already have a really long list of 200 objects that is a bit of a pain to explore. Now imagine if I had a list of 500,000 objects to explore in this right hand panel. So, you know, of course that could be changed, but it just emphasizes the sort of paired challenges where I have many objects which I want to be able to interrogate individually, but they're not really individual objects. They represent a single segmentation run that should be sort of viewed and analyzed in one piece, rather than a big long list of individual cells in an isolated manner. Okay. So the way that we've chosen to represent this is actually very similar to the image data itself. And the reason for this is when you have so many objects on such a large image, we want to follow some of those same principles that we thought about for the image data itself. So I was describing that when I'm all the way zoomed out, I need information across all the tiles, but I don't need really high resolution information. But as I zoom in, I need the highest resolution information, but I need it in a spatially restricted way. And so we want to represent these polygons, these objects, in exactly the same way, okay? And so I'm gonna hop back over to my other image where we've done just that. And so within this region, I'll hide my tissue outline and we can look at the segmentation result itself across the entire image. And as I zoom in, you'll appreciate all of these yellow objects overlaid with the original image data. And so the way that we've represented what looks like now a binary mask, or in some way the segmentation results, is in the same structure that's been specified for image data in OMERO. And so I've just briefly pulled up that specification here. If you haven't worked with this NGFF and OMERO specification before, you can think of this as a complex directory structure that represents the image data as both chunked, so think of those chunks as your tiles, and as multi-scales, so that pyramid of resolutions. It has both that multiple scales representation and the chunks or the tiles representation. And if you have worked with this before, you might have started by working with image data in this OMERO specification. And there is also a specification for labels data. So essentially the same structure as the image data, potentially the same size array as the entire image data, with the same representations of multiple scales and the same chunk size or the same tile size that you see in the image data. Okay. And so this specification is what we're using to represent all of these objects, where you can think of it as another image overlaid with the underlying original image data. Okay, and so it follows the same principles, that I can access the appropriate resolution and the appropriate tiles depending on where I'm looking in that particular viewer. Okay. Any questions so far about this data and that importance of sort of multi-scales and tiles? Okay, so here we're just looking at a single image, and it appears to be a binary mask now, and I can change its opacity to make this a little bit more obvious. This appears like a binary mask. I see, you know, yellow and transparent, but this is actually what I'm referring to as a label image rather than a binary mask. And what I mean by a label image is that we actually have a representation of individual objects, even though this is a single label image. Each of these objects has a unique pixel value, okay? So you think about an individual object ID, it could be 1, and if this was object 1, then every pixel that makes up that object would have the value of 1 within this image, okay? And if this is object 2, then every pixel value within that object would have a value of 2, okay? Any questions there? So here we see this individual label image, but you might do, you know, multiple rounds of segmentation or classification, and you want to represent these together. And so this brings in the idea that it's important to have resolution of individual objects, but you also want to know that all of these objects came from a particular segmentation run. And so that's essentially what we've implemented here. I'm going to keep these as all yellow so that we know that they came from this particular segmentation run. And here what I used was the pre-trained model from Stardist that was pre-trained on H&E data specifically. So Sensible probably matches this data relatively well. But then I also took the pre-trained model that was trained on fluorescence data, and I applied it to this H&E data that had been unmixed. Okay, so we kind of made it look like fluorescence data and then used the fluorescence model. And we did that just to compare, what did we detect with these two different methods using the fluorescence model or the H&E model, okay? And so what you see now that I've turned this one on, this one is in cyan and it's a bit more transparent. And so anywhere where you see a cyan nucleus, that represents an object that was only found with this model here. Anything in yellow is an object that was just found with my H&E model. And anything in green is where you're seeing that overlay of the two. And so it's an object that was found relatively nicely between the two models. And in some cases, of course, slightly different shape. The segmentations are not exactly the same. And so we can see those differences, visualize those differences here. Okay. And so we like this representation because I still can interrogate individual objects, and I'll show you more of that in just a moment. But I can also sort of view these as collections. So all of the objects, all the yellow objects correspond to this single label image, and I know that they were segmented using the same model, and the same is true for this second label image beneath it. Okay, so we think that we've achieved a little bit of the best of both worlds, where we have individual object resolution, but also a clean user interface and the concept of sort of a collection of objects that correspond to a particular run. So I'm now going to hop into talking about how to change the visualization of these objects based on some measurements that you've taken of those objects. So any remaining questions on the OME-ZAR structure itself, what these label images are, anything like that? And
Erin,
yeah, go ahead.
I had a question. So in terms, so you're representing 2D segmentations, but there's nothing in principle that stops this from being used for 3D segmentations?
That's right. So the OME-ZAR specification, you're right, I've been emphasizing X and Y and the downsampling in X and Y. But in fact, the OME-ZAR specification and classically the OMERO image is a 5-dimensional object. So it has a representation of both time and Z depth. And multiple channels. So we're thinking of these label images as single channel, where because each of the pixel values represents the object ID, you might have a high bit depth, but you just need a single channel. But they could have a Z dimension and they could have a time dimension. Now, I think there's some room for how to represent that in a viewer such as this. So this is really designed for digital pathology data, which is commonly just in X and Y rather than having depth to it, but that's not always the case. In OMERO, you can assign ROIs to particular Z sections. And so I think that if you do open 3D data in PathViewer, similar to iViewer, you'll get a slider where you can slide to particular Z sections. And so you could think about this as selectively rendering not only the image tiles that correspond to that particular Z section, but also the label image tiles that correspond to that Z section. But a 3D representation, I think in some imaging domains is even more valuable. And so how exactly you would represent that in a particular viewer, I think there's some room for other input there. This is really designed first and foremost for planar viewing. But the underlying data model is very compatible with 3D data, yeah. Any other questions? I don't know if I emphasized it, but the microservice here is responsible for serving you not only the image tiles, but also the label images here. And that's one advantage for using this OME-ZAR structure, where you have the same structure to your image data as your label image data. Probably a lot of you have had the experience of having a particular format off the microscope where you have your image data, and then you use some really powerful tool like Stardist or Elastic or any number of platforms, and you probably don't get out that vendor-specific file format, you get out something like a TIFF or an OME TIFF or a NumPy array, and matching those together can be a challenge. And so the nice thing about this structure is that you not only have the paired data for your labels and your image, but you also have paired multi-scales and tile representations. And so as you build visualizations of these things, or as you use these as input to some classification model, you know that pulling the same tile from your image and your label image is quite trivial, because it's exactly the same coordinates, if you will, from both. So the access pattern of the data is very streamlined and very paralleled between the two original data and derived data. Okay. So that brings me into the idea of sort of measuring something about these objects and building, for example, a classification. Okay. So one way that we're thinking about this is having this label image represent, the sort of final output of your nice segmentation. I know that I'm gonna, consider all of these nuclei as kind of true and real objects, but I might want to update their visualization based on some measurement that I've taken of them. Okay. And so right now, this is just a series of arrays that represent the labels themselves, the objects themselves. But how do I represent the 100 measurements that I might have on this particular object here, this particular nucleus? And so I'm going to hop back into OMERO Web, where I'm going to highlight two attachments on this image, which represent the OMERO tables that correspond to those two label images, the H&E and the fluorescence model segmented nuclei. Okay, I'll click on one of them here. And so if you haven't used OMERO tables before, they're quite nice because you can even open them up in the browser to visualize your data in kind of an Excel-like view. And I'm going to highlight the first 4 columns here. Okay, so the first is object. And I'm using that to refer to the individual objects within a label image. So I emphasize that the pixel value was encoding the object ID. And so that's exactly what's here. This is referring to the pixels that have the value of 1. This is referring to the pixels that have the value of 2 for object 2. This ROI column is representing the ROI ID. So each of these label images has an ROI ID. Okay, and so to match this row with a particular label image, I use that ROI ID to pair the two. And then probability and area are my 2 measurements. So a fairly simple table here. Probability is the probability of each of those objects. That was an output from the model itself. And then the area, I just measured the area of each of these objects. So for you might have many more and interesting measurements than what I have here, but I'll use these 2 to sort of illustrate the concepts. Okay. And for those interested, this is just a representation of the geometry of that object itself and the tile from which it was segmented, but I won't make use of them today, so we can effectively ignore them. Okay. So in PathViewer, I have not yet gone into the data tab, so I'm going to select this single label image and show how we can take advantage of that OMERO table in the data tab. Okay. So the first thing I'll do is I will select that table. You can see one of them is grayed out because it doesn't have the right reference to the ROI ID. So that second column I emphasize. So it's basically telling me, okay, this is the right table where you have information on this ROI and the objects within it. Okay. And now I want to create a group. And I can use these groups to build interesting visualizations based on that tabular data that refers to this label image. And so the first thing that I might do is I might try and find particular objects of interest. So maybe I want to find very small objects, and I want to color those cyan. And so I'm going to select my area column, and I'm going to add a filter that says the area has to be smaller than some value. Okay. And if I apply that, then I will filter the label image, and now I have just these cyan small objects. But I can also look at the same time at the non-matches. So I can see all the objects, but they're colored in yellow if they didn't match the filters that I put in this group, and they're colored cyan if they are those small objects. And I don't have to just limit myself to a single query. I can add multiple. So maybe I want to make sure that their probability is bigger than a given value. So I don't want to look at small, low probability objects. I want to make sure they're relatively high probability objects. And now I'll find fewer objects in this cyan category by adding this extra filter here. Okay. And so with your, dense, interesting measurements, you can imagine using this to kind of curate interesting, what we're calling label groups. Maybe they're small objects, maybe they're immune cells, maybe they are epithelial cells, and particular thresholds and particular intensity channels, or maybe certain things about the shapes of those cells. So things like circularity measurements might be relevant, size measurements might be relevant. And you can build these kinds of manual classifications to play around with what are the cell types that I have represented here. But importantly, you can also, if you've already generated that data, let's say you have a column that specifies your classification, then you can simply use that column alone to build a visualization. So I'll show you that as well. I'm going to create another group. I'm going to not look at my small cells anymore, and I'm just going to build a specification for this new label group. And this is going to be, I don't have a classification column here, but I'm going to call this probability, because what I'm going to do is now use this color by option where I can choose my probability column. I can choose a color map, and there's a number of options here. And also I'll choose one of them, and then I'll hit apply. And now I'm not introducing any of my own manual filters. I'm just saying, hey, take this column and color by that column. And so probability is a more continuous variable where I have these sliders, and I can move them according to the min and max that I want displayed according to this color map. But you can also think of a string column that has 3 classes in it, or any of your other measurements where you would now color by, and you would automatically get a visualization of that column specific data that you have regardless of the type. And so here I'm no longer looking at the object IDs, and I'm no longer looking at what looks like a binary mask, but I'm instead looking at a color-based representation of the probability of each of my objects. And so the reason that we really like this workflow is you can imagine that you generate your segmented objects and you measure 10 things about them, but then you maybe build a classification workflow, and that's a new measurement of sorts. It's a new column where you want to have the classification of those objects. Or maybe you decide, oh, I forgot to measure the shape parameters. I only measured intensity parameters, and so in my next round I want to measure those intensity parameters. And what you don't want to have to do is duplicate the relatively large underlying label image data that represents the segmentation of all of these objects. It's the same size as the original image data, and you instead want to be flexible in the data table that represents those objects. And on top of that, not only can you add a new table with new measurements or new classifications, what you're doing here is you're building new visualizations based on that data. So instead of first creating your label image that has object IDs as pixel values 1 through 50,000, and then another label image that represents your classes, maybe values 1 through 5 if you have 5 classes, you can generate just a single label image and have a table that tells you your classes, your measurements, and other interesting properties of your data, and change your visualizations from day to day and save them for future use. So we think this is a more flexible way to take that underlying segmentation data, and as your workflow evolves, add new column measurements and thereby update the visualization that you're seeing in PathViewer. Okay. So I will stop there because I know we have 1 minute left, but I'm happy to answer any questions. I know we might get kicked out. I got kicked out last time, but let me know if you have any questions. Might have a chat. is it possible to use your own trained Stardust model in PathViewer? Are there also other options for segmentation? Yes, absolutely. So we are not prescribing any method for segmentation here. And in fact, this segmentation is being done via an OMERO script. So some of you might have used an OMERO script before. These are here in this little gears menu. And these are Python scripts that you can write custom to do whatever segmentation or analysis that you want. We've done things like cell profiler integrations. I mentioned Stardust in this example. Things like CellPose are also very interesting. And so if I have it here, we do have, oops, sorry, it is under analysis. So here, this is run segmentation Stardust, okay? And so all it's taking as input is the channel label, the ROI ID, and then I have a drop down of these 3 pre-trained models from Stardust. And so if you have your own trained model, then you can easily extend this here to have your specific models, or you could even imagine an OMERO script that trains your model for you based on some image information in maybe an OMERO that you want to send off to train your model, and then it would be added here as an option when you run your segmentation. So absolutely, there's lots of possibilities here to use your own pre-trained model or even to use something that's not Stardust. The output essentially has been taken from Stardust and put in this OMERO structure to build these visualizations, but you can bring, elastic segmentation, anything else into that OMERO structure. Any other questions? So I will, maybe if I have time before this runs out, I'll just send this link in the chat. I think I forgot to last time. If anyone hasn't explored that structure yet, I think we'll talk about it across the meeting, but that's a good reference there. Okay. Well, we're gonna get kicked out in 10 seconds. So thanks everyone for joining. Thanks for your questions. Thanks for watching, and hopefully see you at the Hangouts.
Yours?